Hello, it's me, Gogo. We're doing machine learning demonstration. So, data exploration. The data I selected to use for training my machine learning model has already been cleaned and pre-processed to use in such way by Google. The images I extracted from user input for the game Quick Draw have been rendered into a 28 by 28 grayscale bitmap in NumPy format. These images were generated from the simplified data but are aligned to the center of the drawing's bounding box rather than the top left corner. This removes the necessity for the typically necessary pre-processing of data such as scaling and denoising. So obviously the data I'm using it was collected by Google. They did all the necessary pre-processing to be able to use it in a machine learning model. Obviously, if I collected it myself, I would have had to do a bit more cleaning before it was usable. But yeah, that work's already been done, which is why I chose this data set. I don't think there's any ethical concerns I need to mention other than that, yes, this was sourced from Google. I didn't draw a million pictures. Now, in order to prevent the model from being biased towards a specific class, I ensure that the number of images used for each class was the same, which is 10,000. Originally, it was around 100,000 for each class, but I kept running out of RAM on Google Colab, so I had to decrease the number of samples. Still 10,000 for this project will be okay. It will not lead to an underfitted model. There's plenty of images. It's 28 by 28, which is 783 just floating point values. It will be okay. If it was a more complex model, maybe I would need the original 100,000 samples for each project, but for this 10,000, it will be fine. All the features, the pixel strength, they've been uniformly scaled between 0 and 1 as opposed to the original grayscale from 0 to 255. This is because the machine learning model expects floating point values, so had to be scaled down. So while image classification algorithms can be a bit tricky, obviously it's been proven to be possible, making similar thing to what Google did, image classification. Tricky but possible, because we are dealing with classification. Suitable algorithms include SVM, KNN, neural networks like CNN as well. Could have used something more complex as well, like RCNN and other improved versions. But for this project, we're not dealing with anything groundbreaking. These are suitable options. Import everything, obviously, I need mounted to the drive because that's where I keep my data. And I assigned a numerical identifier to each class just to make it easier, faster to train. So split up the 10,000 images. Most of it will go to train, some will go to validation, some will go to test. I did mess around with these values a little bit just to see how it affects the outcome. This seems to be an acceptable split between the numbers. Assert just to make sure that it's no more than one. Floating point errors can be funny sometimes. And then there's a little function just to split the data for me. So loading the data, only use the first 10,000 samples, reshape it. Obviously, this is where I scale the values. And create NumPy arrays with the numerical classifiers for each class. This is all the same. Then concatenate all the arrays into the ones I'm going to need for training. Feature analysis. So I show you the first 100 images of the monkeys just to show you what it looks like. This is what the data looks like visualized. 28 by 28 images of the classes monkey. Cool. So just to make sure again that all the features are correctly scaled, again between 0 and 1, and I create a data frame with all the features and labels for data visualization. So here are all the features, the classes, and I add an extra column for the labels, the numerical classifiers. So apply fit transform to the data. just preparing it to be visualized, and convert the principal components from NumPy array again to a data frame, which is what I will need. You can see the principal components here all the way to the 70,000. This is only working on the train set, which is most of the set. We can examine the variance that the principal components hold, relatively low, which shows good correlation. Shows that indeed classification can be achieved, and project it onto a 2D environment to see the correlation. Now, when we project the two principal components in 2 dimensions, we can observe that points belonging to the same class are closer together in relation to other classes. There is much overlap between classes, however, the data shows correlation between the positioning of the same class. So we can conclude from this evidence that classification is possible once again. Classes seem to form clusters, which is good for classification. There is quite a bit of overlap, but you can see that most of the same class are relatively grouped together. So let's build a model, starting with CNN. I did mess around with this this model, with the layers and how they should be put together, which I'll show you a bit of that later on. I ended up on this, which seems to work quite well. You can see the summary here, and yeah, so define how the loss is. I could obviously optimizer as well, just to increase performance. This is the final model that I am using. There've been previous versions. This is running 30 epochs. You can see accuracy nicely increases, while loss decreases. This tells us that this is not an underfitted model. It's performing quite well, around 98% accuracy. Validation loss remains at an acceptable rate, while validation accuracy remains high, which means it's not an overfitted model. There is a bit of overfitting, around 3%, which I believe is within an acceptable range. I did mess around with the hyperparameters just to decrease the validation loss. I did get it up to a little high for my liking, but I managed to decrease it with messing with the dropout functions and the activation functions. I'll show you a bit of that later. This is what it looks like. It does climb a little bit with 30 epochs. Around 10 it's much lower, which is what I initially used. I increased it to 30 to get a little better accuracy. I'm guessing if I kept running more epochs, the validation loss might climb a little higher, which could lead to an overfitted model. But at 30 epochs, I'm achieving very good accuracy. So it's not necessary for this project. So just to visualize what the confusion matrix looks like, you can see very good classification accuracy. The classes that look similar, there might be a bit of room for error there, such as monkey and the hedgehog could be drawn similarly. That's a problem with animals. People don't really know how to draw animals. Like a washing machine, yeah, it's easy. Do a box, circle in the middle, it's a washing machine. Animals can be a bit tricky to draw. If we look at smiley face, could be mistaken for a potato. Just fair enough, they're both kind of round. These things will just happen when you're working with doodles that people drew, assuming with no art skills. Also created a KNN model to compare different classification algorithms. This one performed considerably worse than CNN, which proves that CNN is a more suitable algorithm for this problem. Even after tuning the hyperparameters, it still wasn't as good as the CNN. I'll show you a bit of that later. Here are some previous versions of me messing with hyperparameters. Just sigmoid didn't perform well at all with the activation function there. As you can see, not good. Problem is when I put these images in, I had them in order on my PC, but Google kind of messed up the order. But in the live demo, I can show you them one by one. So at 10 epochs, it was doing okay. But when I increased it to 30, the validation loss climbed up a little bit, which is when I started messing around with the dropout layer. Again, increasing the dropout rate, it can help prevent overfitting just by getting rid of so I think it's not like exactly half if I put 0.5 in. It's just on average 50%. It does it randomly, so again, no guarantee that it'll always be the same, which once again can help prevent overfitting. So once again, validation loss does climb a little bit, but through some fine tuning, I did get it down to a little less than what is here. I ended up settling on ReLU. I tried TanH, CellU, Sigmoid, Softmax, which are all here, but you can look at these. I don't want to waste too much time going over them one by one. I summarized my findings further down the line. Yes, so best activation function, ReLU, CellU was okay, TanH was okay. Increasing the pooling seemed to affect the performance in a positive way. Adding extra dropout layers negatively affected the accuracy somehow. So I went back to the original 2 towards the end of increasing the dropout percentage, decreased validation loss, also a little bit of the accuracy, but if it can help prevent overfitting, it's acceptable. And as I increased the epochs, the accuracy again went up, validation loss also went up, the loss decreased steadily. So again, this could point to potential overfitting, but messing with the hyperparameters helped a little bit. Overall, we're looking at the evaluation of the model. It clearly shows that it performs at exceptional rates at identifying classes accurately. Around 98% accuracy with low loss factor proves that the identification is to a high standard and the model is not underfitted. I managed to decrease the validation loss while keeping a high validation accuracy through, once again, fine-tuning the hyperparameters that you can look at the pictures for more information. It helped me achieve a less overfitted model. Observing the confusion matrix, we can tell that the classes performed under average compared to other the animals, which people might find a bit more tricky to draw. Could contribute to some false negatives. When looking at the comparing the CNN to the KNN model, you can see that it performed considerably worse. You can see while tuning the parameter n neighbors, it still couldn't achieve the 98% accuracy that the CNN was able to. And once again, the accuracy on the test set is a little lower than what it is on the training set, which means that this is still as well just a little bit overfitted. But it tends to happen, I suppose, because there's more information in the train set than the test set. Lovely.